Hello, in this lecture we are going to discuss how first-order optimization algorithms, such as ADAM, can be used in practice to train neural networks. Let us first make a step back and discuss what it means to train a neural network. Training a neural network f, x, theta, where theta is a vector containing weights and biases, is equivalent to solving the following optimization problem. Compute the parameters theta that minimize the expectation of the loss with respect to the data distribution of the problem, where L is a given loss function and P data is the data distribution of the problem. For instance, in the case of image recognition, P data associates the correct class, say cats or dog, to each image. In literature, this expectation is called risk. In practice, the data distribution is generally unknown, and even if it were known, computing the resulting expectation would be infeasible most of the time. Therefore, we approximate the risk with the empirical risk, which is just an approximation of the risk via a set of data, which we collect in a dataset D. In practice, the expectation is approximated with an average from sample of the data distribution. Now, the question is, how can we minimize the empirical risk? To minimize the empirical risk, we would like to use variants of gradient descent such as ADAM. All of these algorithms require to compute the gradient of a neural network for a given data point with respect to all parameters, which can be done by backpropagation. However, for the large dataset used in practice, this is often expensive, as it means running the backpropagation algorithm ND time, where ND is the size of the dataset. To understand this point, recall that the gradient of a sum is a sum of the gradients. Hence, to compute the gradient of the empirical risk, we need to compute the gradient with respect to all the data. A solution to this is simply to use a mini batch of the theta at each iteration, which is just a subset from the data randomly sampled from the dataset. This is the rationale behind gradient descent. If the size of the mini batch is much smaller than the dataset size, this means a great gain in efficiency. Note also that if NB, the size of the dataset of the mini batch, is still large enough, we can still obtain an estimate that is good approximation of the risk. In fact, the average will still be a good approximation of the expectation. Following this intuition, the stochastic gradient descent algorithm samples a mini batch of data from the dataset at each iteration. Then it performs the gradient update using a first-order optimization, say ADAM. And then it keeps repeating this process until a stopping criteria is met. The stopping criteria is generally a maximum number of iterations or a threshold of the obtained accuracy. Note that while it may seem a relatively simple algorithm, SGT with ADAMs works very well in practice. Before concluding this lecture, let's talk a bit more about the optimization problem behind training a neural network. First of all, we should note that in general, a neural network is a non-convex function. As a consequence, when you compose a neural network with the loss, you obtain a non-convex function. This leads to a non-convex optimization problem, for which the global optimum can in general not be found. If you look at the slide, you can see, for example, the loss of a neural network, which does indeed look very non-regular and may seem extremely hard to optimize. In fact, given that a neural network is a non-convex function, when you optimize it with stochastic gradient descent, in theory and also in practice, many problems can arise. For instance, you can get stuck in local minima that are far away from the global one. There may be regions with vanishing gradients or even saddle points, which are critical points that are neither minima or maxima. So you may think, then there is no hope to train neural networks with hundreds of millions of parameters. In practice, however, the techniques that we discussed do tend to work surprisingly well on finding good local minima that are close to the optimal one. While this has been shown empirically by the tremendous success of neural networks in the multiple applications, it has also been confirmed mathematically in recent papers. This paper and this research is outside the scope of the lecture, but if you are interested, feel free to get in touch. In particular, it has recently been shown that in the limit of infinitely many parameters, the loss of a neural network do tend to become a convex function, thus explaining why training neural networks with a lot of parameters such as those used in practice tend to work quite well. Thank you for your attention. I hope you really enjoyed this video and have learned a bit about neural networks and deep learning.